Hello and welcome. In this video tutorial, we're going to be working through Skills Practice 20.1 waves. Please remember to pause or rewind the video as needed. A wave is something that's going to carry or transfer energy from one point to another point. The high point of the wave is called the crest. You can see that in the picture below. The low point in the wave is called the trough. You can see that in the picture below down here. So there are, in this picture alone, there are 3 crests and 1, 2, 3, 4 troughs. The amplitude of the wave is the distance from the crest to the trough divided by 2. So if we take the whole distance across the wave and cut it in half, we have the amplitude. So our amplitude I'm going to highlight with a marker as the distance from the middle equilibrium to the highest or lowest point. The wavelength is the distance from one point of the wave to the next corresponding point. So from crest to crest would be one wavelength, or from trough to trough, there's another wavelength. Or we could go from this point here to when we repeat again to this point here. You can see this distance is the same as this distance, which is the same as that distance. Okay? So we have several ways of measuring the wavelength. Okay, now we remember back from the beginning of the school year that the speed of anything is measured as the distance divided by time. Now, if we focus on the speed of a wave, let's focus on wave properties within this equation. And the speed of the wave would be the wavelength, that would be the distance. Okay, and for those unfamiliar with this variable, this symbol is the Greek letter lambda, and it stands for wavelength. So the distance is going to be the wavelength. The time for one wave would be the period. So wavelength divided by period. Now, one thing hopefully we remember from last week is that the inverse of the period, 1 over the period, is the frequency. So that's where this equation comes from here, wavelength times frequency. Okay? Now recall, anytime you see meters per second, we're given the speed. Anytime we're given hertz, that is the unit of frequency. And anytime we're given meters or centimeters, possibly, that is the unit of wavelength. Let's go down to question number 1. On the graphic to the right, following parts of the wave, let's identify one wavelength, half a wavelength, amplitude, crest, and a trough. All right, so well, let's see what we're looking at here. This from here to here would be one wavelength. But do keep in mind, there's other ways you could have mentioned this. You could have gone from crest to crest. Notice the distance between those lines are the same distance between these two right here. You could have also gone trough to trough. You could have also gone from here all the way to here. All of those would essentially measure the wavelength. Okay, but I'll choose to do that first picture. Now, half a wavelength would just be half of that. So from here to here would be half a wavelength. Top part of the wave would be the crest. Bottom part of the wave would be the trough. The amplitude would just simply be the distance to the highest or lowest point from equilibrium. What is the amplitude of the wave above? Well, The distance from 0 either way would be 5 centimeters. Now in question number 2, we need to create a graph that has a wavelength of 1 centimeter, an amplitude of 1 centimeter and a wavelength of 2 centimeters. So we're going to create the same scale for both graphs. So let's go ahead and scale. We're going to go every 2 boxes is 1 centimeter. Same thing on the bottom graph. Okay, so now to create an amplitude of 1 centimeter, we got to go higher or lower. 1 centimeter higher or lower than 0. 0 is the equilibrium. So go 1 centimeter higher or lower than that, and I'll place a dot right here at 1 centimeter. Now I need to repeat that dot every 2 centimeters. In other words, we're going to create one wave every 2 centimeters. I'm going to make another dot every 2 centimeters down the line. Now I can go to -1, which is the other end of the wave, every point in between those top dots. And you can complete your wave by drawing a nice smooth curve between those dots. Okay, and we can see we have an amplitude of 1 centimeter. We can see the wave repeats with a wavelength every 2 centimeters. In part B, similar idea, but different information. So we're going to go with a height of 1.5, and we're going to repeat this every 3 centimeters. Which means the other amplitude is going to be the halfway point of those top blue dots. So we're going to go down here, here, and here. Complete the nice smooth curve that connects those dots. And you would have a wave that repeats with a wavelength of every 3 centimeters. And you can see the amplitude is measured at 1.5 centimeters. Now in questions 3 through 9, we're going to be taking a look at actual wave speed problems. Okay, now to do a wave speed problem, we're going to need the use of 2 things throughout the way. Number 1, we're going to need the use of our wave speed equation. Speed of the wave is equal to frequency times wavelength. The other thing we will occasionally need is the idea that frequency is the inverse of the period, and the period is the inverse of the frequency. So be prepared to use these tools as we go through. As always, the first thing we do is read and annotate. Number 3, a water wave has a frequency of 2 hertz and a wavelength of 5 meters. Calculate its speed. Anytime you're given hertz, you're given frequency. Anytime you're given meters for a wave problem, you're given wavelength. We're looking for speed. We use the question mark. F is 2 hertz. Lambda is 5 meters. And the equation we need is frequency times wavelength. For this one, it's a straightforward plug and chug because we're already solved for speed. It's just a matter of plugging in for that. So we're going to plug in 2 hertz for frequency and 5 meters for distance, and we are looking at 10 meters per second. Okay. Now, why meters per second? Well, if you remember, V is equal to frequency times wavelength, but that's the same thing as wavelength divided by period. Because remember, 1 over the period is the frequency. So the unit of wavelength would be meters, the unit of period would be seconds. So you can see how the unit of meters per second would still show up for speed. Number 4, a wave has a speed of 50 meters per second and a frequency of 10 hertz. We are given the speed and we are given the frequency. We're looking for the wavelength in this problem. We're still going to use our wave speed equation. The difference this time is we need to actually solve the wave speed equation for wavelength. You can accomplish this by dividing both sides by wavelength would therefore be the speed over the frequency, and now you can go ahead and plug in your numbers. 50 meters per second over 10 hertz, or 10 cycles per second, would be 5 meters. Number 5. A wave has a speed of 30 meters per second and a wavelength of 3 meters. Calculate its frequency. We are given the speed, we are given the wavelength, and we are looking for that frequency. Update your information, keep yourself organized using the same equation. This time we need to take that equation and we need to solve it for F, the frequency. This can be done by dividing both sides by lambda. And frequency would be the wave speed over the wavelength. So frequency is going to be equal to 30 meters per second over 3 meters, which would be 10 hertz or 10 cycles per second. Number 6, a wave has a period of 2 seconds. Well, period is t. And it has a wavelength of 4 meters. That's lambda. We want to find the frequency and the speed. So we are given a period of 2 seconds and we are given a wavelength of 4 meters. Now this is going to be one of those problems where we have to use our inverse. Recall that frequency is the inverse of the period. So to get frequency, we're going to go 1 over 2 seconds, or 0.5 hertz, or half a cycle a second. Now to get the speed, we're going to use our wave speed equation, in which case we will go 0.5 hertz times 4 meters. Well, half of that would be 2 meters per second. Now this can be done another way. Recall, wave speed is frequency times wavelength, but it's also wavelength divided by period. So you could have taken the 4 meter wavelength and divided it by 2 seconds, and you still get 2 meters per second. So I do want you all to see that there are multiple ways of accomplishing this. Number 7. We have a sound wave traveling at 330 meters per second. This would be the speed. Has a wavelength of 2 meters. That would be lambda. We're looking for frequency and we're looking for period. Label your given information. First, since we're given speed and wavelength, we can use the wave speed equation to figure out the frequency. That can be done first. So wave speed is equal to frequency times wavelength. We're solving for frequency, so we'll divide by the wavelength. And frequency is speed over wavelength, which is 330 meters per second divided by 2 meters. And we would get 125 hertz. Now, to get the period from this, we also need the fact that the period is the inverse of the frequency. And we're going to go the inverse of 125. So put in your calculator, 125 inverse. And you're going to get a really, really small number, 0.008 seconds. In other words, 8/1000ths of a second is how long it takes for that sound wave to, get to the next wave. Traveling pretty fast. Number 8, we have a frequency of wave A is 250 hertz and a wavelength of 30 centimeters. The frequency of wave B is 260 hertz with a wavelength of 25 centimeters. Which wave is faster? Well, in order to figure this out, we should probably organize our work between wave A and wave B. With the given information and the unknowns. Now, to find out which wave is faster, you need to calculate the wave speed, but you need to do it for both waves. So we're given that wave A has a frequency, or excuse me, I'm sorry, we're looking for the wave speed for both. We are given wave A has a frequency of 250 hertz. We are given that wave B has a frequency of 260 hertz. We are given the wavelength of wave A is 30 centimeters. If we move the decimal 2 spots to the right, the wavelength is 0.30 meters. And for wave B, moving the decimal 2 to the left, the wavelength is 0.25 meters. So if we split this up, we look, wave A is going to have a speed of 250 times 0.3. Which is about 75 meters per second. Okay. Now, if you left the units in centimeters, that would be fine. It's just you would have 750 centimeters per second. So please make sure that if you did not change the unit of wavelength, that it's reflected in the unit of speed. Okay. Now, the wave B, okay, you're going to be going to 260 times 125, which is 65 meters per second. Clearly, wave A is faster. And finally, question number 9. The period of a wave is equal to the time for one wavelength to pass a fixed point. You stand on a pier watching water waves and you see 10 wavelengths pass in 40 seconds. What is the period? What is the frequency? And if the wavelength, lambda, is 3 meters, then what is the wave speed? Okay, so we're looking for these things. Now we're also given this information here, which is 10 waves in 40 seconds. Okay, or you could have written it the other way, 40 seconds for 10 waves. Either one works. All right, well, I'm going to actually start with this. You see, 40 seconds for 10 waves would be 4 seconds for one wave, which would just be 4 seconds. That, ladies and gentlemen, would be the period. Period is 4 seconds. Okay, we're taking 4 seconds to repeat every wave. Okay. Now, the frequency can be found by going 1 over the period, or 1 over 4 seconds, or 0.25 hertz, a quarter of a cycle every second. Part C, we're going to go to frequency times wavelength to finish off this problem. So frequency is 0.25 times the wavelength of 3 meters, and 0.25 times 3 is 0.75 meters.